Hello everyone, I am Dr. VRAO. From the lecture 56 of thermodynamics, we got awareness on path functions, reversible and irreversible processes, and various formulas for calculating the work done in different cases. And in this lecture, we are going to learn about internal energy. After this, we can go for first law of thermodynamics, because first law of thermodynamics involves path functions, two path functions and internal energy. Now coming to the internal energy, right? Internal energy. Right? What is internal energy? Every substance or every system, right? Every substance or every system. So, every substance has fixed quantity of energy. Every substance has fixed quantity of energy, or every system has a fixed quantity of energy, right? Which depends on chemical nature and state of existence. I repeat, every substance has a fixed quantity of energy, or every system has a fixed quantity of energy, right? Which depends on chemical nature and state of existence. This is called intrinsic energy or internal energy, right? So, every substance has a fixed quantity of energy, or every system has a fixed quantity of energy, right? That energy is called internal energy, which is represented by a letter U, or in some textbooks it represented by E, right? So, U or E, that is internal energy. And internal energy, and there are different kinds of energies involves in internal energy, right? Internal energy is every system or every substance has a fixed quantity of energy, that is called internal energy, and that internal energy involves various forms of energies. The various forms which contribute to internal energy are translational energy, vibrational energy, rotational energy, nuclear energy, bond energy, etc., etc., etc. So, various forms of energies contribute to the internal energy. Therefore, internal energy, that is total internal energy or internal energy of the system involves, that is, we can write internal energy of the system is, you can write U, or internal energy U system, or internal energy of a substance U system or E system, whatever the letter you want to assign for the internal energy, right? So, this internal energy, various forms of energies contribute to internal energy. Those are U translational energy, that is internal energy due to translational energy, and internal energy due to vibrational energy, and energy due to rotational energy, and energy due to nuclear energy, and energy of bond energy, so etc., etc., etc. So, all these forms of energies contribute to total energy. That is internal energy constitute, or internal energy consists of all these kinds of energies, right? So, Therefore, internal energy is a algebraic sum of various forms of energies that which includes translational energy, vibrational energy, rotational energy, nuclear energy, bond energy, or another some other type of energies. The algebraic sum of all those energies are called as internal energy, right? So this internal energy is constant. This energy is different for different systems. Okay, this energy is different for different systems. Already I told you every substance is a fixed quantity of energy, right? For example, if you take 1 mole of carbon dioxide at a density P, 1 mole of carbon dioxide at normal temperature pressure, it has some internal energy, and that internal energy is different for 1 mole of SO2 gas, SO2 at NTP. Okay, so 1 mole of CO2 at NTP has a certain amount of internal energy, and that amount of energy is different, and similarly, or you can say that 1 mole of SO2 at NTP has another amount of internal energy. Okay, so that means it is a fixed quantity of energy, and it different for different systems, right? 1 mole of CO2 has certain amount of energy, for example X amount of internal energy, and that 1 mole of SO2 at NTP has another amount of energy, that is Y amount, but these two are not same, So this is about internal energy. So internal energy is a state function. Internal energy is a state function, which means that it is impossible, that is, it is not possible to calculate the exact value of internal energy. Because why we are unable to calculate exact value of internal energy? Because internal energy involves various forms of energies, and that forms of energies, and we are not able to calculate that forms of energies exactly, right? So internal energy is a state function. State function means, already I told you in the beginning video of thermodynamics, internal energy is a state function. State function means which depends on initial and final states of this system, right? So we cannot calculate the exact value of internal energy, but we can calculate the change in internal energy, that is internal energy at the initial state and internal energy at the final state. Thereby we can determine the change that occurs from initial state to final state, right? So internal energy is a state function. Okay, and exact value of internal energy cannot be calculated, as it involves various forms of energies, and it is not possible to calculate all kinds of such energies exactly, right? So therefore internal energy, and moreover internal energy depends on temperature, pressure, volume, and quantity of matter, right? Internal energy depends on temperature, pressure, volume, and quantity of matter. Therefore in nutshell, internal energy is energy stored in a substance or energy stored in a system at a constant temperature and pressure. Only this point, you should remember this point in your mind, that is, internal energy is energy stored in a substance or energy stored in a system at a constant temperature and pressure, right? So that is about internal energy, right? So internal energy, and we got aware of internal energy and two path functions, that is work and heat. Now we can go for first law of thermodynamics, that is first law of thermodynamics. First law of thermodynamics. Right? Already I told you laws of thermodynamics based on 3 generalizations, and the first generalization is you never get something for nothing. Right? You never get something for nothing. Therefore, and first law of thermodynamics, this law can be stated in different forms. Okay, and we can give the different statements for first law of thermodynamics. First statement is energy neither be created nor be destroyed. It is the very fundamental statement. We have been going by listening this statement, that is energy of conservation. Energy neither be created nor be destroyed, but we can convert or we can transform one form of energy into another form of energy. Right? So, energy neither be created nor be destroyed, but we can transform that one form of energy into another form of energy. This is one statement for first law of thermodynamics. There is another statement, another important statement for first law of thermodynamics, that is it is very important, that is it is impossible to construct a perpetual motion machine of a first kind. I repeat, it is impossible to construct a perpetual motion machine of a first kind. What is a perpetual motion machine of a first kind? That is, perpetual motion machine of a first kind is a one, that is a machine, that is a one which operates in cycles, right, which operates in like a Carnot cycle, right, which operates in cycles, and that can produce work without the expenditure of energy. Right? Perpetual motion machine is one which operates in cycles and can produce work without the expenditure of energy. That means, without the expense of energy, that machine can do work. Is it possible? It is not possible. That is why first law of thermodynamics rules out the existence of rules out the construction of a perpetual motion machine of a first kind. How can we create the perpetual motion machine of first kind? That is a machine which operates in cycles, of course, and can produce work without the expenditure of energy. How it is possible? Without the expenditure of energy, can we do work? No. Without the expenditure of energy, we cannot do any work, because work is a form of mode of energy transfer. So, without energy transfer, we cannot do work. Right? So, it is impossible to construct a perpetual motion machine of a first kind that operates in cycles and that can produce work without expenditure of energy. Therefore, first law rules out the construction of a perpetual motion machine of a first kind. So, that is the statement of first law of thermodynamics. It is nothing but a simple, we can say this first law of thermodynamics in a simple generalization. Already I told you, you never get something for nothing. You never get something for nothing. Right? For nothing, we cannot get anything. Right? So, that is the simple generalization that we can give for first law of thermodynamics. Right? now we go for mathematical equation for first law of thermodynamics, right. For example, let us consider a system. Let us consider a system. Already I told you every system has a fixed quantity of energy. Already I told you every system has a fixed quantity of energy, and that fixed quantity of energy is called intrinsic energy or internal energy. So, now let us consider a system. Let us consider a system whose internal energy is U1, whose internal energy is U1. Let us say whose internal energy is U1. Now, we are supplying Q amount of heat to that system, that is, we supplied Q amount of energy to that system. What happens? Internal energy of this system increases. Already I told you, when we Q takes the positive sign, that is, when Q amount of heat is absorbed by the system, that means we are giving energy, in the form of heat. Already I told you, energy means in entire, when we concerns with thermodynamics, energy means that is heat energy. So, when if the system supplied Q amount of energy, that is, if we supply Q amount of energy, what happens? Internal energy of the system increases by amount Q, right. So, when we supply Q amount of energy to the system, internal energy of the system increases by the amount Q, because Q is also a form of energy, right. And if for example, if work done on the system, already I told you sign notation for work and heat. Work done on the system, if we do work done on the system, means W take the positive sign, that means work done on the system, that means work done, when we do work done on the system, that means energy of the system further increases. Work done on the system means energy of the system further increases. Okay. Now, let us suppose work done on the system, then that is work done on the system, then internal energy of the system further increases, and that equals to U2, Okay. So, all this internal energy, initial internal energy of the system is U1. We supplied Q amount of heat. By that Q amount of heat, internal energy of the system increases, and after that we do work done on the system, and work done on the system also raises the internal energy of the system, and the total and final internal energy of this system becomes U2. Therefore, you can write U2 is the internal energy of the system at final state, and U1 is the, you take this U1 into on this side, U1 is the internal energy of the system at initial state. U2 minus U1, that is Q plus W. U2 minus, this is the change, that is delta U. You can write that change as delta U. So, delta U is equal to Q plus W. This is the mathematical formulation or mathematical equation for first law of thermodynamics. Delta U is equal to Q plus W. Delta U equal to Q plus W, where W is work done on the system, because W take the positive sign here. W take the positive sign here. For example, if work done by the system, then what happens? System loses some energy. Okay, and that and that W take the negative sign, that is delta U. Now you can write Q is equal to delta U plus W. Delta U plus W. This is in the case of work done by the system. Work done by the system. This is work done on the system. This is on the system. This is work done by the system. Right? Right? You can understand this first law of thermodynamics from this equation. That is Q is equal to delta U plus W. Q equal to delta E plus W. That is when Q amount of heat is supplied to the system, that is useful to increase the internal energy of the system and also useful for work done by the system. And also work done by this system, because most of the in an entire thermodynamics, most of the cases we are always concerned with work done by the system. Work done by the system. So you can understand the first law of thermodynamics from this statement more easily. That is, when Q amount of heat is supplied to the system, that heat energy is useful to increase the internal energy of the system and to do some work, that is work done by the system. So what is the generalization we discussed? We never get something for nothing. Okay? If you are not supplying this Q amount of energy, system does not increase its internal energy and system does not do any work. But if you supply Q amount of energy, system can increase internal energy and that heat energy is useful for the work done by the system. Right? So you never get something for nothing. But if you supply Q amount of energy to the system, that is useful for the internal energy and work done by the system. Right? So this is about first law of thermodynamics, but there are three cases in first law of thermodynamics. That is, take the first law of thermodynamics. That is, for example, system does not undergo any change in internal energy. That is, delta U is equal to 0. Delta U is equal to 0. Delta U is equal to 0. Take this delta U equal to 0. Take this equation. Delta equal to 0. First case 1 is delta U equal to 0. That is, system does not undergo any change in internal energy. That is, delta equal to 0. Then delta equal to 0, this first law can take the form delta Q plus W equal to 0 and Q is equal to minus W. What it indicates, what it concludes? Heat absorbed from the surroundings. Here the Q take the positive sign, that means heat absorbed from the surroundings is equal to work done by the system. Work done by the system, right? Okay. Q take the positive sign here, that means heat absorbed from the surroundings or heat absorbed by the system is equal to work done by the system, because W take the negative sign, right? So that is the case 1. And case 2, for example, system does not do any work, that is W is equal to 0, that is W is equal to 0. Then W is equal to 0, what is the then first law of thermodynamics take the form Q is equal to delta U. W equal to 0, that is work done by the system, or work is 0, then Q equal to delta U, right? Delta U, right? Delta U. What it represents, what it concludes, because work done by the system, here Q take the positive sign, that is work heat absorbed by the system or heat absorbed from the surroundings is equal to increase in internal energy. That is, heat absorbed by the system increases the internal energy of the system, because they take the positive sign, right, and heat absorbed by the system increases the internal energy of the system, or heat lost by the system. For example, this is positive sign and this is also a positive sign, that is heat absorbed by the system, that increases the internal energy. Heat lost by the system, internal energy decreases, right. So, heat absorbed by the system, internal energy of the system increases. Heat lost by the system, internal energy of the system decreases. Okay, that is the second case. And the third case is case 3, when Q is 0, that is when Q is 0, that is heat absorbed by the system is 0. Okay, when Q equal to 0, when Q equal to 0, when Q equal to 0, delta E equal to delta U equal to W, delta E equal to W. Okay, that means Q equal to 0, that means this is adiabatic. Q equal to 0, that is heat transformed between system and surroundings is 0. Okay, where it happens? In case of adiabatic wall. Okay, because adiabatic wall because the system and surrounding heat occurs through conducting wall, which constitute the boundary between system and surroundings. When Q equal to 0, that is conducting wall does not allow heat flow between system and surroundings, that is Q is equal to 0. Q is equal to 0 means that is the adiabatic wall, and this work is adiabatic work. This is adiabatic work. This is adiabatic work. So, Q equal to 0, that is adiabatic work, that is internal energy increases or is equal to change in internal energy is equal to adiabatic work. Adiabatic work. And the for in case of gaseous states, in case of gaseous molecules. Okay, in case of gaseous systems where gas expands against external pressure, then Q is equal to PdV, then W is equal to PdV. You already we discussed this. In case of gaseous systems, W is equal to PdV. That is, in case of gaseous systems, gas expands against external pressure. That is work done by the system, then W can take the form minus PdV. This is called mechanical work or pressure volume work So, Q minus PdV, that is this can first law can take the form Q minus PdV is equal to delta U. Okay. For example, if change in volume is 0, that is at a constant volume, change in volume is 0, that is gas does not expand any, gas does not expand, that is change in volume is 0, that is dV is 0, that is this term becomes 0, that is at a constant volume, there is no volume change, that is constant volume. This is dV is equal to 0, that means dV is equal to 0 means that equation take the form dV is equal to delta U, that is heat absorbed at a constant volume, is equal to internal energy of the system, right. Heat absorbed at a constant volume is equal to a change in internal energy of the system, So, this is about internal energy and first law of thermodynamics, right. So, in the next video we will learn another concept. I hope you all understand the first law of thermodynamics, right. If you really like this video, please extend your support by like, share, comment and subscribe. Thank you for watching.